a natural exponential function. So we want to ask ourselves a question, right? We want to ask ourselves a question. So remember when we looked at our little student loan example, as we compounded more and more and more, um, we got closer and closer and closer to a bigger number, right? But we didn't know what that bigger number is. But some economics or some mathematician wanted to figure that out. And so I said, okay, let's just pretend we had an interest rate of 1, so 100%, right? And we're going to compound it for we're going to have it run for 1 year, and we're going to see how many times we compound it, right? And so here, if n was 1, and if I compound it if the interest rate was 100% after 1 year, it'll double, or 1 over 1 over 1. So this would be 2 to the first power, which is 2. And they said, okay, let's compound it twice, and that was 2.25. And then I said, okay, let's compound this like 100 times. And that was 2.70481. And that's like, let's do it 1,000 times. 1,000 times was 2.7169. And they said, let's just do it 10 to the fifth. Right? And so here they're just compounding it more and more and more. And they realize this number, 10 to the sixth, and let's do 10 to the seventh, and we'll call it good there. They realized that this number was converging to something else. 7 and then 2.718. And this is literally how this number is defined. E is defined to be this if I take the limit as n goes to infinity, right? 1 plus 1 over n to the n. This is literally how that's defined. And for you people in calculus, you know exactly what we're doing here. We'll just take n as it gets infinitely large, take the limit of that. Well, that's defined to be e. E is an irrational number. It doesn't repeat. There's no real method to it. It's just this way thing. E appears in a lot of things. In a lot of things. It's called the natural exponential, just because it appears. Oh, I'm trying to think of other places I say it, and then my brain just. You ever say something, open up the file drawer that you know is full, and you're just looking through all the folders and they're just blank, and your brain's just not pulling up a single case where you know this happens. So it appears a lot. We use it, it happens a lot in math, it appears in differential equations, and therefore it appears in, other things. Um, so, anyways, this is natural exponential function, so we call this e to the x. Sometimes known as the exponential function. So if they say the exponential function, they're talking about this one, right? Just how it is. And so here, I guess I never graphed it. This is what I wanted this one. So here, let me just show you. And then here you can do a bunch of these where you move it around. Let me just show you how to do that real quick. So here, e to the x, well, e looks a lot like 2, right? Let's just put a little 2 and put an e here. Boop. So e looks a lot like 2. Go ahead and get rid of that. So e looks a lot. So here's 2 to the x, here's e to the x. So it's really close to that. It just hits a little bit different marks. So as we move it around, we're just going to do the same thing I taught you how to do last time. So if I type in e to the x minus 1, I'm just moving my point from the 0. It still goes through 0, 1, because it's still an exponential function. I'm just going to move it down 1. And then here, if I have e to the, what's the other one I do? X plus 2. Nope. Try and do it that way. Okay. Here, we're just going to take this. We're going to take it and we're going to move it over too. Okay. So you just move. It's the same thing as before. The exact same thing as before. Nothing terribly interesting here. So here, I'll graph e to the x right here. So e to the x looks something like this. And so e to the minus 1x is just going to move this point down 1, put it right here. Okay. And so we're going to just move the 0, 0, and there's still the and so the asymptotic line goes down by 0. And then for this one, we're just going to move it over 2. So put it here, pretend that's your new point, and it comes out, goes up, and goes through. Okay, so it's not horribly, terribly interesting. It's just the same. So let me just write here, same as before. They do a whole section, so it goes through the whole rigmarole again. I'm like, we just taught it, and it's literally doesn't follow any different rules at all. Not even a little bit. So, usually if I'm using E, roughly in my head, I use 2.718, right? Or 2.7, depending on how rough I'm being. Okay, so let's go to our last page for the day. All right, so this is the example I pulled. Then it became a lot more real. I remember teaching this because I taught 126 right after the pandemic started, and I was sitting there teaching this, and people were like, "Too real, man, too real." So let's pretend we have an infectious disease that spreads in a small city with a population of 1,000. After T days, the number of population infected is given by this formula. Okay, and this is actually close to real. To real. This is actually close to what it actually, how infections actually run. It gets a little bit more complicated after this, but often you'll see this naturally. So how do we do this? Well, we type this into a computer. You do not crunch these numbers. You just don't. So let me show you how to do that in Wolfram Alpha. All right, so here we're going to type this. Hey, I want you over here. There we go. All right, so we're going to type this in Wolfram Alpha. So how would I type in this piece? So here, let's type in the top. Since the top's a single number, we're just going to leave it like that, and then hit that parentheses 5 plus 1, 2, 4, 5 e raise parentheses, and so this would be negative. Oops, I forgot my negative sign. Negative 0.097 t, and so t we're going to change. We're going to start it at 0, so we'll plug in times 0, and we'll close it and close it. See if it looks like what we want. Okay, and so here we have this. Now, a number of infected people. Well, we can't have a partially infected person. I guess you could, right? I'm just going to round these to whole numbers. Going to say someone is or isn't affected. Depends on how you want to say that. When it comes to this infectious disease and infection, usually they determine that if you have X amount of the virus or the bacteria or whatever, that's an infectious amount. And so I think it was like, I don't know. I don't know. It's gonna bug me. I'm gonna look it up. Uh, uh, I'm not gonna get that. Oh, here it is. Hold on, let's see if I can find this real quick. I don't want to show a whole bunch of it. Now it's really low. It's not going to tell me. There's what they call a need for infection. So if we're here, we're just going to put in 8, right? So at day 0, according to this model, 8 people are infected. All right. And let's just go ahead and plug in the other numbers real quick. So we'll just do 1 and 2. I'll show you 1 and 2, and then we'll go from there. The way infectious diseases says, usually there's what they call an infection threshold. You have to have X amount of the virus in you to be infectious. And so here at 1, I wrote this in wrong, didn't I? It should be 4 and 5. Then here, if I plug in 8, there's 0. I get 8 even. Aha! I get 8 even. Here, if I plug in 1, I get 20.97. And so it depends if you want to write that way. So 20.97, you can say someone's about to be infectious or whatever. And let's just fill out the table. And so you just go ahead and just swap out that one number, and you can fill out this table of 135 or 137, 6, 7, 8. But how a disease works, I think you need like something like, it's either like, it's a lot. It's like anywhere between tens of thousands, somewhere around tens of thousands, give or take, a magnitude of 2, which sounds terrible because that's it's like somewhere between 100 and a million viruses, right? Before you get infected. And so that's why we took the precautions that we did. It's just to reduce that number. Anyway, so this is how an infectious population goes. And so here, the number of people infected given a pretty infectious disease. So I'm being very careful not to go too much into it because I'm not supposed to be political. And I don't know how an infectious disease became political, but it has. And so therefore I better not touch it. Just put it that way. Let's just put it that way. All right. So here we could graph this, and let's go ahead and graph it ourselves, and then we'll use Desmos to graph it and see if our graph's not better than Desmos's. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, perfect. I was being smart when I made this. 1, 2, 3, 4. 1, 2, 3, 4, 5. Bam. 1, 2, 3, 4, 5. And so this is 10. All right, so we're going to graph days on this graph. We're going to graph number of infected people. So number of people infected. Okay. All right, and then we're going to do, to make this graph make sense, we need to get to about 2,000. So 1, 2, 3, 4, 5. So we'll say this is 1,000, and then 1, 2, 3, 4. Nope, we're not doing 5. I didn't make it that tall. 1, 2, 3, 4, 1,000. 1, 2, 3, 4, 2,000. Okay, that's fine. So here, day 0, we're at 8 people, doesn't even really register. This would be 250. So not quite there, still not quite there. We're over 250. In fact, we're up at day 5. So here, day 3, we're still at 100. Day 5, we're a little bit over the halfway point. So we'll say here. And then by day 8, we're way up here. And then day 10, we're about here. And so it kind of looks something like this. Okay. All right. So let's graph this thing. Let's graph it in Desmos. Hi, Desmos. You're not going to like this graph. You're just not. So, let's see if I can make this work a little better. Okay. Let's put it in X. Desmos is happier about it. Let's get rid of this. I don't know why it has that there, and put this there to make it. There we go. All right, so here we have our graph. We're gonna have to zoom out. Okay, so I like our graph a little bit better by changing the scale so it's not even. Basically, it just goes pound, right? That's what it looks like here. Here we can see it's a somewhat of a change up to our threshold of infection. Okay, um, and so this is a better example of like the flu virus, where here you can say about a fifth the population is immune to being infected, right? For whatever reason. Um, the difference between our current pandemic is that no human ever, there was no inherent immunity, right? No one's ever seen it before. Um, and so when it went around, nobody had had antibodies for it running in their system. And so that's why ours ran a little different. Okay. So this is quite common. You'll see natural exponents just pop up everywhere. Okay. All right, so let's just do this last little part and then we'll get to what we did. So let's talk about compounding interest. And so that's what the real world uses. This is a lie. They don't use this. They just don't. Science uses this. Math does not. So real world uses aka. So let me switch out the real world. Yeah, this is just a lie. I was like, oh no, this is what they use, right? Because I remember saying no, it's not. So I need to remove that. So that will be removed in these notes. Okay. So here, let's do, if we want to compound something interest. So we're going to have the same thing as before, our same student. And here we're going to do the 3,000 or the 30,000. And now it's going to be E. And so if we just run this continuously, that means that every microsecond, in fact, between every microsecond, we're compounding the interest, right? Um, and so let's pretend, I don't know if I complain. So if I compound a 10% interest 10 times a year, that means at 10 even intervals, I'm gonna calculate 0.0. I'm gonna do 1% interest, recalculate my principal, and then and at another 10%, at another 10, 1/10 of the year, I'll compound 1% interest, recalculate it, and that's what it means to compound. Okay? So this means continuous means I can always do this. And so at any time, it's acted like I've always just constantly added every tiny bit of interest back into the principal. All right, so our rate here is 0.07 and our time here is 4. Okay, and so now the rate goes in a different spot instead of being it, um, as I read, it comes out and goes here. Okay, so it's slightly different. You just crunch this through a calculator and it'll give you that number right here. All right. And so this is 3,900 and 993.89. Okay, so it's not that much higher than everything else, um, but it is higher still. All right, that's the end of the notes. Your homework will deal with some of these compounding stuff, so you'll have to compound normally,